Hello, good morning, sir. Engineer Aboyasir Manalindo. I am Vanessa May Viloria, and I am going to present to you first our foundation proposal together with my partner, Miss Rose Diane Sukayan. So you can see here our proposed four-story commercial building with 25 by 30 lot area or building area with 30 commercial spaces and with complete facilities such as male and female toilet, the elevators, storage rooms, and electrical rooms. Next, you can see here the destination or location of our building. It is located at the Mosa District, JP Laurel Avenue, Lanang, Davao City. Our isolated footing design subjected to concentric load with biaxial bending. So why we use biaxial bending? Because we have two moments here, the MX and the MY, and the concentrated load PY. So here in our next slide, we can see our isolated footing location. So what I've said a while ago, it is located in our frame G here, the highlighted part. And when you zoom it in, you can see this one. So it is designed an isolated footing because it has enough spaces to occupy its dimensions, footing dimensions, and this part here, the frame G, has loading that is enough for a design of isolated. So in this column here, we can see the corresponding nodes of that columns. So for our first column or footing, we have the node 2, next 46, 47, 48, 49, node 56, 50, and 3. So in these 8 nodes, we will choose the top 5 isolated footing designs for a total of 40 isolated footing designs. So next here is our isolated footing design calculation. So as I will explain this one, we will go to our Excel part. So I will use the node 2 for this explanation, and the other nodes is just the same calculations of this first node. Here is our footing 2 or node 2 isolated footing design calculations. In this sheet, it is named as tabulations, for it contains the tabulations we will use for the calculations. So in the first column or first tables, we can see the factored load combinations, numbers 14 to 89 here. So this factored load, we will choose later on the top 5 also for our calculations for the shear and flexure. Now, below is the unfactored load combinations. So it starts from 90 to 137. So we will use these unfactored loads for our calculations for the stability or for the measurement or dimensions of our footing, the base and the length. The base and the length. So in our calculations, we will use the PY or FY here, the MX for our moment at X axis, and the MZ for our moment at Y axis. So for our calculations for the stability, we will go to this sheet. So as an example on how we compute this solution, we will use the load combination 90. And for the other combinations, it is just the same as this load here. So first, we will be needing our parameters. So we need the Q allowable or the soil bearing capacity allowable, the PY or the P unfactored, the MX unfactored, and the MZ unfactored as our MY. So for our Q allowable, we have here 190 kilonewton per meter squared. It is an assumed value. Next is the PY equal to 296.535 and MX 2.024, MY is 5.523. So we use the absolute values of these parameters. And solving for our ratio, we have L is to B is equal to 1 because our footing design is a square footing. So length and base is just equal. Next, for solving for our footing dimension, we have this formula for our soil bearing capacity allowable equal to the P total over the base times length plus 6mx over length times b squared, base squared, plus 6mz over base times length squared. So substituting the values of py, mx, and mz, we have this equation, our expression. So solving that one, finding the value of b, we can arrive with this answer, 1.320 meters. So once again, our ratio is L is to B. So our dimension for B and L is just the same. So checking for its safety, first we will check for the capacity, and we will be having the formula of P is equal to, P allowable is equal to the Q allowable times the effective area. So for our effective area, we will be using our effective length and effective B dimensions. So for our effective length, we will use this formula here. L prime is equal to L minus 2 EY. So for our EY, it is equivalent to MY or MZ is MZ over the P total. MZ here, 5.523, and the P total, 296.54. So substituting the values, here we can arrive with the answer of 1.283 meters for our effective length. Next, for our effective base, it is equal to B minus 2EX. So for our EX, we will be having MX over P total. So substituting the values, we can arrive with the answer of 1.306 for our base prime, or effective base. Recall, our formula for checking for the capacity is P allowable is equal to the Q allowable times the area effective, or length times B effective. So substituting the values, 190 times 1.283 times 1.306 will be equal to 318.364. So our for the safety measures, we need the P allowable to be greater than the P actual. So 318.364 for our P allowable is greater than our Q allowable, which is 190 kilonewton per meter squared. So therefore, it is safe. And for our stability checking, we will use the formula of our Q allowable here. It's just the same, except for the signs, which we will use is the minus or negative. Because later on, if the answer is positive, it will be safe, for that is a indication of a compression. And for the compression, it means that no uplift pressure is present in our soil pressure. So substituting the values, Q mean is equal to the P total over our dimensions, the product of our dimensions, minus 6mx times the length and B squared, minus 6 times my over our base times length squared. So we will arrive with the answer for our Q mean equal to 150.58704. So it is a positive answer. Therefore, it is safe and no uplift pressure is present with our footing. Therefore, we will use these dimensions for our load combination 90, which is 1.32 times 1.32 millimeter squared area. So this calculation is the same as this, and all our load combinations unfactored. Next, we will see in our tabulations and factored that it has been ranked from top 1 to top 49, I guess. So for our top 1, we have the here. We have the load combinations 122. And for our top 2, we have the load combinations 136. For our top 3, we have the 125 load combination. And for our top 4, we have this 120 load combinations. And lastly, our top 5 is 115. So to summarize, we have this table here. And you can see the load combinations of our top 5, the PY of our top 5, MX and MZ, as well as our calculated base and length. To further see our top 5, we will go to this sheet, stability top 5. For our top 1, the load combination 120 with the footing dimensions of 2080 by 2080 millimeters squared. For our top 2, we have the load combination 136 and footing dimension of 2080 by 2080 millimeters squared also. And for our top 3, we have the load combination of 125. And for the dimension, we have 2075 by 2075 millimeters squared. For our fourth one, we have the load combination 120 and the dimension of 2074 by 2074 millimeters squared. And lastly, for our top 5, we have the load combination of 115, resulting to the footing dimension of 2065 and 2065. So it's all safe, 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 and safe also. So going to our shear and flexure, we have this load combination also. These parameters is from our factored loads because for our design for shear and design for flexure, we will use the ultimate parameters or loadings. So for our top 1, we have these solutions. I will explain it later. And for the top 2, top 3, top 4, and top 5, it is just the same process. So, yeah. Has the same process, so I will not explain it. So for our top 1, we have these columns here, or tables. For our calculations, we will need the F prime C, Fy, the concrete cover measurement, and the diameter of our bars, steel bars. So for our F prime C, we have 21 MPa. Sorry, the neighbors are too loud. And Fy is 275 MPa. For our concrete cover, we have 75 mm. And for our steel bars, we use the 25 millimeter diameter. So for our computation of soil pressure, we have this formula. Q ultimate is equal to PU ultimate, P ultimate over BL plus or minus 6 MUX over B length squared plus or minus 6 MUZ over L B squared. So substituting the values, we arrive for this expression here. And for our soil pressures, the values here varies because for the sign here at our equation, it will be basing with our direction for the rotation of our MUX and MUZ. So when it's going towards the side of that soil pressure, it will be positive, but when it goes under or on the other side, it will be negative. So for our calculations in solving for one-way shear, we will draw our diagram or picture for our soil pressure. So we have the footing here and the soil bearing capacity, which we have QUA as the largest, QUD as the second one largest, QUB is the third one, and lastly the smallest is the QUC. So connecting that one, we have this image here and our column here, C1, C2. So we will be having for one-way shear, first is parallel to B. So parallel to B, largest part here is this one, this part here. So this is X and this is L minus X. L minus X. This is our one-way shear parallel to B. So projecting downwards, we have QUA here, QUA, QUA, Q1UA, QU1A, and this one is QU1B. So this part here is projected as this part, the back part is projected here. So this is the image of the back part. L here as our length, L minus X, and this is X. This is our X also here. So to solve the distance for our X, we have this formula, L minus C. L minus the C, or the dimension of column, divided by 2, so that it will leave this part. L minus C divided by 2. It will leave this part here. Yeah. Minus D. So this is our D. And we will arrive with this answer, 0.79 minus D. So to get the value of QU1D, we will be having this formula or this expression here, substituting the values of our QUA and QUD. So QUA minus QUD is equal to the length and equal to QU1A minus 188.14 all over this distance here, which is the length, or 2.08 minus X. So it will leave this distance. And we will get the value of QU1A equal to 198.95 plus 8.37D. Next, for this part here, to get the value of our QU1B, we have this figure. The same as the value of X, we have 0.79 minus D. So using the formula of similar triangles, we arrive at these equations here, 41.23, which is here, minus 23.81 over the length, 2.08, is equal to QU1B, minus 23.89 is equal to this distance, which is 2.08 minus 0.79 minus D. That will lead us to the value of QU1B equal to 34.615 plus 8.37D. Next, we will get the average of this four here, QU1B, QU1A, and QUA here, and QUB here. So the average is, we will get the sum of this divided by 4, which will lead us to the answer of 120.091 plus 4.1869D. To get the value of our depth, we have the formula VU is equal to phi VC. So for our VU, we have the formula of our QU average times our X. This is our X, 0.79 minus D, times our 2.08, which is our length, or the B. It is the base, measurement of the base. So for our VVC, we have the formula of 0.75, it's our safety factor, times 0.17 times square root of the f prime c, which is 21. So the answer is 4.6 times the base times the d times 1000 for the conversion. So we will arrive at the answer of 0.14 meters for our depth. So for our section 2-2, we take the side of BA because it has a larger soil pressure, the same as our one-way shear at section 1-1. So for our x, we have this equation, b minus c all over 2 minus d. We will arrive at the same answer, 0.79 minus d. So for getting the value of QU2A, we will be using the similar triangles again. So 205.57 minus 41.23 equal to this length, which is 2.08, is equal to QU2A minus 41.23 all over this value, or this distance here, which is equal to 2.08 minus the x, or 0.79 minus d. So we will arrive at the answer of QU2D equal to 143.15 plus 79D. Next, for getting the value of our QU2B, we use this by similar triangle. So 188.14 minus this value all over this length is equal to QU2B minus this value here over this length for our second triangle. So the answer for QU2B is equal to 125.72 plus 79D. So again, getting the average, QU average of that part, section 2.2, 2-2, it will be equal to 165.645 plus 39.494D. And we will be using this formula for getting our D. So again, substituting the values here for the formula of VU and VBC and equating that to, will be getting the value of our D is equal to 0.19 meters. So for our two-way shear, we will be having first this formula, the QU average for the whole soil pressure of our footing. So QUA plus QUB plus QUC plus QUD over 4, we will be having 114.688 kilonewton per meter squared as our QU average. So for our BO, we have 2 times C1 plus D plus 2 times C2 plus D is equal to 2 plus 4D. This BO is used later on. We will be using this later on for our VVC formula. So next, we have here again our equation, VU is equal to VVC, to equate two formulas here to get the value of D. So for our VU, we have the formula of QU average times the area minus the side of the column, distance of the side of the column, or C1, plus D and square. So for our VVC, the same safety factor, 0.75, while this is different, 0.33 times square root of f prime c, which is 21, times our BO here, this one, times the D times 1000 for the conversion. We will be arriving at the answer of 0.16 meters. So comparing the three values of D, we will get the largest value, which is 0.19, because the two other is 0.16 and 0.14. So the largest is 0.19, so we will use D is equal to 190 millimeters. So for our thickness, we will be having this formula, D plus diameter of our bar over 2 plus our concrete cover, which we will lead to the answer of 277.5 millimeter. So we will round this up and we will get the value of 280 millimeters. So we have the depth and the thickness. Next, we will design for our flexure. So for our flexure, the same as the one-way shear and process, we will be using the larger value or average of the soil pressure under. So for the flexure parallel to B, we have this figure, and like the one-way shear, we don't have minus D here because our design for flexure is like this one. So the shaded part is near or on the column, so we will not subtract D from it. So this part here is our X. This is B. And projecting downwards, this is our Q3A and this is our Q3B. So that is our value for our X, 0.79. And using again the similar triangle, for getting QU3A, we will be arriving at the answer of 198.95 kPa. And the same as the other side, Q3B, we will get the answer of 34.615 kPa. So QU3 times X for our P1 is 157.22. And for our P2, we have 0.5 times 0.79, or our X, times 205.57 minus 198.95. So this is our area 1 and area 2. Area 1 can be located here. And area 2 can be located under. It is in the shape of triangle. So P total is 159.83. And for our X, A, we will be having the formula here, and it is called the Varignon's theorem, which is P total times X bar A is equal to area 1 times its X, or centroid plus area 2 times its centroid also. So the centroid of this one, of our area 1, is between this one, our X, for our area 1. And for our area 2, we have this one here. That is our X. So, getting that value, we will arrive at the answer of 0.397 meters. Next is, for the second part, Q3P, we have here our area 1, our area 2, and our P total. Then, solving for X bar by Varignon's theorem, we have the area total times X bar is equal to the area 1 times its X plus area 2 times its X. So, the answer for our X bar B is 407 meters. And then, we will use this one, XA and XP, in getting for our X bar, which is just the average of the two. So our X bar will be 0.402 meters. So getting the average of that part of the flexure, QUA plus QUC plus Q3A plus Q3B over 4 is 120.091 kilonewton per meter squared. So using this value here for our QU average and the X bar, we will use these values in our MEY, which is QU average times the X times the B times the X bar. So we will arrive at the answer of 79.36 kilonewton meter as our moment of our Rn, equal to MUy over the safety factor of 0.9 times B in millimeters and depth in millimeters squared. So we will arrive at the answer of 1.1741 MPa. So this Rn is used in this formula of our rho. So for the formula of our rho, we have rho is equal to 0.85 F prime C times our, or over our Fy times 1 minus square root of 1 minus 2 Rn all over 0.85 F prime C. So substituting the values of F prime C, Fy, our Rn, and F prime C again, we will arrive at the answer of 0.004420 as our rho. We will erase this one first. So for our rho mean, we have the formula of 1.4 all over Fy. Fy is 275, so we will arrive at the answer of 0.005091. So using this, comparing this value, we will use the larger value, and for this two, the larger value is rho mean, which is 0.00509. So substituting the value of rho mean in our AS or area, rho mean times B times D, we will be having the answer of 2012.4022. So solving for our number of bars, we have the formula of AS over pi 4AS, that is 4AS here in the numerator, all over pi d squared in the denominator. So we will arrive at the answer of 4.0996. So rounding this up, we will be having 5 bars of 25 millimeter diameter bars. So for our spacing, we have this formula, B minus 2 times concrete cover minus the diameter of our bar all over the number of bars minus 1. Substituting the values of that variables, we will arrive at the answer of 476.37. So in our spacing, we will round it down. For rounding it down is safer because it will give our bars the distance, the right distance for it to carry the loadings. So therefore, we will use 5 bars of 25 millimeter diameter bars spaced at 470 millimeters. Next, for our section 4 parallel to L bars, we have these figures here, this and this part. We will get the answer of QU4A and QU3A first. So we will arrive at the answer of 143.15 as Q4A and Q4D, it's Q4D, sorry, 125.72 kilonewton per meter squared. By using similar triangle, we arrive at that answers. So our X is just the same, 0.79, and for our P1, it is located again here, and for our P2 is our triangle part here. So for our first area, we have this part here, which is rectangle, and for the second one, it is a triangle below here. And we will get its P total, which is 137.78. The same goes in this part here, A1 plus A2, and the P total is 124.02. So solving for our X bar by Varignon's theorem, we will be having the P total times X bar D is equal to the A1 or area 1 times its X plus area 2 times its X. So we will get the value of 0.419 meters for our barred X. And the same goes with the other part, and we will get the bar xc equal to 0.421. So getting the average of that bar x, we will be having the answer of 0.42 meters. So we will also get our QU average, QUA plus QUC plus QU4A plus QU4D is equal to 165.645 kPa. And substituting these values to this formula here to get our MUY, we will be having the answer of 114.38 kilonewton meter. So for our Rn, substituting MUY in our numerator times 10 to the 6th power so that it will give us an answer of MPa all over the safety factor of 0.9 times B times our depth, which is 190 millimeters squared, and the answer is 1.6922. So for our raw, substituting the value of Rn, F prime C, and Fy to our formula, we will arrive at the answer of 0.006477. So for our raw mean, it is the same, 1.4 all over Fy, so it will be equal to 0.00509. So comparing these two values here, the larger value is the raw, so we will use the value of our raw, which is 0.006477. Substituting that raw value in our formula for our area, we will arrive at the answer of 2,560.1236 millimeters squared. So getting the number of bars we will be using for the bars parallel to L, it is 4AS all over pi times D squared. So we will get the answer of 5.2154. We will round that up so that it will be safer. And for our spacing, we have B minus 2cc minus our diameter of bars, which is 25, times all over our number of bars minus 1, so 6 minus 1. We will arrive at the answer of 381.1. So it will be round down to 380 millimeters to be safer. So therefore, we will use 6 bars of 25 millimeter diameter bars spaced at 380 millimeters. So that is the process for our shear and flexure design, and the same goes to the other dimensions or designs of our footing. Top 1 to top 5 of every nodes of the isolated footing. So that is it for our calculations for our isolated footing subjected to concentric load by biaxial bending. So here we can see our schedule of square isolated footing designs. We have a total of 40 different designs for our isolated footing image or model for our detailing in our isolated footing design. So this is df, or the depth of our footing, and for the thickness, it is located here, the thickness of our footing. And for our plan, we have the length here, the base here, C1 or column dimension, C2. And for our transverse rebars, steel bars, we have this counting. 1, 2, 3, 4, 5, 6. That is the transverse bars or the bars parallel to B. And for our longitudinal rebar steel bars, structural bars, we have this bars here. This is our top 5 for our node 2. 2.08, 2.08 dimensions, 2.75, 2.75 dimensions, 2.07 times 2.07, and 2.07 times 2.07. So for our node 3, you can see our top 5 design footing for isolated design. Next is the node 46. This is our top 5 for that node. For our node 47, our node 48 for isolated footing design, and for our node 49, node 50, and lastly our node 56. So that is the end of my presentation, And my partner, Miss Rose Tayan Sukayan, will continue for the strap footing and combined footing. Thank you.